Okay, hello. I think we are ready to get going. Welcome to this next session called Emotion, Singing and Voice Conversion. I'm Simon King from the University of Edinburgh. And I think we have our first presenter online. Konstantinos, would you like to make yourself visible? Hi.
Hello.
Welcome. So first paper is from the Samsung group. Konstantinos will present. And the paper is Rapping, Singing, Voice Synthesis based on phoneme level prosody control. Over to you.
Hello, my name is Konstantinos Markopoulos, and I will present your paper entitled Rapping, Singing, Voice Synthesis based on phoneme level prosody control. Our work focuses on building a text-to-rapping singing system which can be adapted to any speaker's voice. This system utilizes a tachotron-based multi-speaker acoustic model trained on read-only speech data and provides prosody control on the phoneme level. Dataset augmentation and prosody manipulation are also investigated in this work. This model can also be fine-tuned to an unseen speaker's limited data recordings, allowing rapping and singing with a target speaker's voice, even on different language. In recent years, many steps have been made towards high-quality singing voice synthesis, or SVS, with the use of neural and deep learning methods. Hybrid, mixed, and conditioned models have been introduced that advance further the SVS systems. Some notable approaches are the wavenet variant architecture used for parametric singing synthesis, WGAN-Sing, which is a pitch condition generated by the adversarial network, and an adversarially trained pitch condition sequence-to-sequence Korean singing model introduced by Lee in 2019. Another GAN-based approach was introduced in 2020 by Polyak, which uses additional perceptual losses on its generator output. Some other work worth mentioning is Mellotron, which is a multi-speaker expressive voice synthesis model based on GST Tachotron 2. Jukebox, Utaco, and Durian SC should also be mentioned. Transformer architecture has also been employed to SVS, as in Deep Singer and Hi-Fi Singer, which include a fast pitch-based model. One of the latest approaches is ByteSync, which is a Tachotron 2 model combined with a duration prediction model and uses linguistic along with musical embeddings. The main difference between our approach and other SVS systems is that all the models mentioned are trained on singing data. In our approach and our contribution is to produce songs by using only speech data. Mellotron is the only SVS model that uses speech data, although used in a different way, so we will compare our approach to this one. We propose a complete text-to-rapping and singing approach based on a system that relies solely on spoken data and can be adapted to an unseen target's voice with very limited data. This method is based on a previous work on a fine-grained prosody manipulation multi-speaker TTS model called Improved Prosody Clustering for multi-speaker and speaker-independent phoneme level prosody control. Combined with training data augmentation, our method can achieve phoneme-level prosody manipulation in pitch and duration, which allows us to generate rapping and singing synthesized song. The training dataset consists of speech data in US English and Korean languages spoken by 7 male and female speakers. For the case of speaker adaptation, we resume the model training on new speakers of both languages with a limited amount of spoken data and show that the resulting models can also maintain the same prosody control capabilities. Extracting the desired prosody information from a given a cappella song and presenting it as input to our model enables us to synthesize a cappella utterances that closely follow the reference, allowing rapping and singing synthesis with the voice of every speaker, including in the training set. Our approach is depicted in this block diagram presented in the slide and will be analyzed thoroughly. This block diagram consists of 4 main parts. The first part involves the preprocessing of the lyrics by a front-end module in order to obtain the phonemes, as well as the extraction of the required prosodic features, phoneme durations and pitch, from the reference audio. Phoneme alignments are automatically extracted from the song using an HMM monophone acoustic model trained using flat start initialization. Some manual corrections took place on long vowel durations in the singing data that are not usually encountered in speech. Pitch contours are calculated using the Pratt toolkit, and interpolation is also applied on the unvoiced regions in order to avoid 0 values, and the final contour is smooth. The second part is the note conversion and extraction. The acoustic model is trained to control the prosody within the range of each speaker. When a reference song is used as input to the proposed system, the pitch contour of the singing speaker may have different range than that of the target speaker. This is due to the fact that the song originates from a different speaker with diverse source characteristics or gender. Also, the singing speech itself may vary in extreme F0 values both in the lower and higher end between two speakers. For that reason, we use the equation shown in the slide in order to transpose the F0 contour of the reference speaker to match the range of the target speaker. There were two approaches examined on pitch transformation. The first one takes one single global pitch value for the reference speaker, which is the median pitch value, while the second recalculates the median F0 value for every verse. The first approach works better, producing more stable samples and avoids the discontinuities in octaves that may occur due to the calculation of the F0. After the conversion, the average phoneme level F0 is calculated by using the previously extracted alignments. The corresponding musical note and octaves can be extracted by the next formulas that can be found in music theory. In the third block, the converted F0 values along with the phoneme durations are discretized and used by the TTS model, which produces the synthesized song by controlling the prosody at the phoneme level. As already mentioned, we use an acoustic model based on previous work. This method uses unsupervised clustering on phoneme level in order to extract a sequence of discrete learnable prosodic labels for each utterance, which is then used to condition the decoder of a tachotron-based acoustic model in parallel to the phoneme sequence. The model is also augmented with a secondary mixture of logistics attention module, which operates on the prosodic sequence only, aiming to disentangle the phonetic and prosodic content. The final model is able to control the prosody at the phoneme level, both for F0 and duration, while maintaining high speech quality. Following the procedure of the previous step, the notes and octaves are assigned to separate learnable embeddings so that any possible combinations are modeled appropriately, even the ones that don't exist in the training set. This global representation of musical notes is also speaker independent, being suitable for our multi-speaker setup. For the duration labels, we used an improved and more stable method than k-means introduced in our previous work. And what we did was the following. We sorted the values in ascending order and grouped them into a desired number of intervals so that an equal number of samples is contained in each interval. This helps with the problem of voice quality deterioration in extreme values, which are not common in the training set, while slightly decreasing the duration control range. We have experimented with two different setups, one with 15 and another with 30 duration labels. The acoustic model is trained with an internal multilingual multi-speaker dataset containing over 200 hours of speech in both US English and Korean, containing speakers of both genders in order to capture as many prosodic patterns as possible, which will help increase the range of the model in both F0 and duration. That way, each speaker has the capability to rap or sing a wider variety of songs. Augmentation is also employed both in F0 and duration by applying pitch shifting and tempo alteration respectively, further increasing the quantity and range of training data. The different speakers are assigned a learnable speaker embedding, which also conditions the decoder at each step. We also use a linear adversarial speaker classifier on the phoneme encoder outputs in order to make them speaker independent, as well as a residual variational encoder, which captures other latent features of the recording. For the speaker adaptation, we found that freezing the weights of the phoneme encoder, prosody encoder, and the attention module yields better results. We can account this to the fact that the model has already learned rich representations, which must not be forgotten in the adaptation stage by the target speaker's limited data. The next step is the post-processing step. The prosody control model produces a cappella utterances, which are derived between silence tokens from the original lyrics. These utterances must be concatenated in the time domain in order to obtain the full verse of the song. Additionally, the duration values are discrete in our model, resulting in some form of quantization, hence the final durations may not exactly match the original song. The accurate matching of the synthesized song with the original requires lengthening or shortening of speech, which is performed by Wazola and Piazzolla algorithms. Two types of evaluation took place. Regarding the objective evaluation, clips from 4 rap songs and 4 songs, all sung a cappella in English, were used as ground truth. All the proposed models, along with Mellotron, were evaluated against these ground truth a cappella songs. As shown in the left figure provided, the synthesized pitch contours closely follow the reference ones, while they are shifted appropriately in order to match the F0 mean value of the inference speaker of each model. In the next figure, it can be also observed that the F0 contours of a reference and synthesized clip, illustrated in this MIDI-like graph, follow the same pattern. As an objective metric for measuring the accuracy of our approach, we calculated the average distance of F0 and duration between the reference and the synthesized audio on a per phoneme basis. F0 values of the reference audio were transposed again so as to target the speaker's mean F0 value before calculation of the distance. It was observed that there is no significant difference in these metrics between speakers seen in the training set and those used only for adaptation, neither on F0 nor on duration values. This is valid for both 15 and 30 duration label models. Mellotron seems to achieve an F0 contour slightly closer to the reference. Overall, our method manages to reproduce a cappella singing with accurate pitch and duration phoneme values, especially in cases where the respective a cappella reference audio is straightforward, without notably long durations or extreme low or high notes. In the latter cases, we noticed that our approach did not accurately produce phonemes with a target F0 or duration values, leading either to attention failures or duration mismatches with the reference audio. Regarding the subjective evaluation, a formal listening test took place. 2 clips from songs and 2 clips from rap songs, all in English a cappella, were used as ground truth, and the respective audio stimuli produced by our system and Mellotron were rated. In the framework of this subjective evaluation, aside from the overall quality, we also opted to assess the effect of the number of duration labels per phoneme and the effect of the post-processing stage for duration matching to the reference audio via Wazolla. 60 listeners participated in this MOS test. The average MOS score with 95 confidence interval for each voice model versus song type and post-processing method are presented in the table shown. The results show that our approach provides satisfactory output equally for both rapping and singing, even if the latter is considered as a more complex task. Overall, post-processing for matching the word boundaries between ground truth and audio stimuli does not seem to provide any consistent and robust improvement. It was also observed that the 15-class duration labeling improves singing, which is most probably attributed to the fact that fewer but more populated classes in training entail better learning for our model. Moreover, the adapted speakers achieve similar quality results with the speakers who are seen during training. This is prominent, especially for English, where the adapted voice performs equally well to the rest of the English training set voices, while at the same time the Korean adapted voice follows closely the performance of the Korean training voices. Regarding the comparison with Mellotron, it was observed that Mellotron output is melodic, but often bears intelligibility issues or audio artifacts. This observation may justify why Mellotron scored lower compared to our system in the formal subjective evaluation. Nevertheless, Mellotron outperformed our approach in a test song where vibrato singing was prominent, a voice characteristic that Mellotron can capture and transfer well, in contrast to our approach where only F0 and duration values per phoneme are provided. So, to wrap up, in this paper we presented an approach for producing high-quality singing and rapping synthesis from a tachotron-based fine-grained prosody control voice model trained solely on read data. Even though its results do not match the output of an SVS system trained on singing data, our approach achieves satisfactory results in both singing and rapping. Experiments showed that equally good singing synthesis can be achieved for limited data target voices via adaptation. The system, although it can provide satisfactory results for rapping and simple songs, it may fail to produce adequate singing for more challenging songs with wide variations in both note values and duration. Further research on controlling singing voice characteristics such as loudness and vibrato, as well as on including singing data in the training process, is taking place at the moment, as long as to fully automate some manual parts of the proposed process. And here are some samples. There are 2 songs and 2 rap songs. This is the ground truth, for example.
You only need the light when it's burning low. Only miss the sun when it starts to snow. Only know you love her when you let
And this
her
is
go.
our female voice.
Well, you only need the light when it's burning low. Only miss the sun when it starts to snow. Only know you love her when you let her go.
And
well, you only need the light when it's burning low. Only miss the sun when it starts to snow. Only know you love her when you let her go.
And this is the ground truth of Jingle Bells.
Oh, jingle bells, jingle all the way. Oh, what fun it is to ride in a one-horse open sleigh. Hey, jingle bells, jingle all the way. Oh, what fun.
You got the idea? This is the male speaker.
Oh, jingle bells, jingle all the way. Oh, what fun it is to ride in a one-horse open sleigh. Hey, jingle bells, jingle all the way. Oh, what fun it is to ride in a one-horse open sleigh.
And our female speaker.
Oh, jingle bells, jingle all the way. Oh, what fun it is to ride in a one-horse open sleigh. Hey, jingle bells, jingle all the way. Oh, what fun it is to ride in a one-horse open sleigh.
The same happened with the rap songs. This is the ground truth.
His palms are sweaty, knees weak, arms are heavy. There's vomit on his sweater already. Mom's spaghetti, he's nervous, but on the surface he looks calm and ready to drop bombs.
This is our male speaker.
His palms are sweaty, knees weak, arms are heavy. There's vomit on his sweater already. Mom's spaghetti, he's nervous, but on the surface he looks calm and ready to drop bombs.
And the same with the female speaker.
His palms are sweaty, knees weak, arms are heavy. There's vomit on his sweater already. Mom's spaghetti, he's nervous, but on the surface he looks calm and ready to drop bombs.
And the last is another rap song.
Can't change the world unless we change ourselves. Die from the sicknesses if we don't seek the help. All eyes be my witness when I speak was felt. Full house on my hands, the cards I was dealt.
Can't change the world unless we change ourselves. Die from the sicknesses if we don't seek the health. All eyes be my witness when I speak what's felt. Full house on my hands, the cards I was dealt.
Happens, sorry. And you know, there are many samples available in the link provided. You can access them if you scan the QR code or by the link. So that's all. Thank you very much.
Okay, thank you very much. I'm going to start with questions in the chat. We'll give people in the room a chance. So Javi asks a good question. What exactly was the question that you asked the listeners when they evaluated this? Were they told that it's speech or singing or rap? What was the wording of the question?
The question, the listeners were asked to just listen to the song and see how close it is to the original, so to the ground truth song. So yes, that was the question. How close is that? We didn't say anything about speech or singing or stuff like that. Just how close one song to the other is.
Okay, I have my own sort of follow-up to that. I noticed in the kind of conversion of F0 and in the samples, it's clear that the output is not in tune. It doesn't quite closely follow the tune. So in the way you're sort of shifting things, at the very least, you're changing the key and possibly not actually following the tune quite so closely. I didn't fully understand how this sort of F0 conversion was working.
Yeah, we used, excuse me.
I see that you're sort of rounding to the nearest musical note, yeah, but there wasn't any guarantee that you're hitting the right note.
Excuse me? Yes. So we took the target speaker and the reference speaker who have a different mean pitch. We use median. And, you know, we through the first equation shown, we transposed the pitch contour to match, all the notes to the base frequency of the target speaker. So we took the median and used this equation, and we found, the mean pitch of the target speaker. Yes, the whole track, the whole notes were transposed to each key. So it will be not the same key. There's no significance on the key, but only in the the relationship between the notes of the target speaker.
Sure. Okay. I'll let people in the room in Budapest ask questions if anyone would like to come forward. While they're thinking about that, someone else has put something in the chat. Yeah, I think it's also a follow-up from Javier. What about the vocoder? So first of all, what vocoder did you use? And then kind of the obvious question, can the vocoder reproduce, the note that you're asking it to? Is the vocoder partly responsible for staying in tune or going out of tune?
No, the vocoder doesn't play any part on this. It's only the front end. The acoustic model plays. We've used in LPCnet as a vocoder, but all the work is done on the acoustic model, not on the vocoder.
I think Javier is asking, is it possible that the vocoder does not generate the F0 that's been asked to? Could it introduce errors? Or did you test that the vocoder, always generates the F0 of the spectrogram being put into it?
Yes, in some cases where there is vibrato and high notes or very low notes, yes, the vocoder doesn't succeed. So we have to transfer all the song to another scale. Yes, but these, you know, they're not, the vocoder works perfect on the.
Yeah, we'll finish with one last question in the chat. We've got to squeeze this one in before we move on to the next presentation from Adriana Stan. She's asking that, you know, in your F0 conversion, I think the target speaker is guaranteed to produce a musical note through the rounding. Yes. But of course, the source speaker might not be. Singers don't sing in MIDI notes. They can sing any frequency they like. So how do you deal with that in the conversion? I think she's asking.
I didn't exactly understand.
So singers don't just sing the notes on the piano keyboard. They can sing anything in between. They can do glissandos and things.
Yes, we didn't did anything on that. We just take a, you know, it's like a tachytone-based model. So we assign to every phoneme a note, an octave, and a duration. These are quantized values. So yes, there may be some, you know, some variations between them. But you doing that in phoneme level covered these variations, and the produced audio was good enough, as it seems.
Right. Okay. I don't see any.
The idea was to use only speech data and not singing data, which is easier to do that. But you know, it was a challenging problem using speech data.
Got it. Great. I think we've filled up the available time. So thank you again for the presentation. I don't see any questions in the room. And so thank you, Konstantinos. We're going to move on to the second paper in this session. I'm going to invite Jennifer Williams to reveal herself and unmute. A paper from NII and University of Edinburgh entitled Exploring Disentanglement with Multilingual and Monolingual VQ-VAE. Jennifer, whenever you're ready, go ahead.
Okay, hi everybody, thank you, Simon. So I'll be presenting this paper on disentanglement with multilingual and monolingual data. I'm Jennifer Williams, I'm from Edinburgh, the Center for Speech Technology Research, Simon's student. Actually, this is also a collaboration with the National Institute for Informatics with Erica Cooper and Junichi Yamagishi, as well as Jason Fung. So some of the motivations for this work are to learn, of course, disentangled speaker and phone representations primarily, but also to try and adapt a trained monolingual English VQ-VAE model to multilingual data, and in this case, German, English, French, and Italian. And then the primary focus of this paper is to evaluate the performance in downstream tasks. The gist being that these tasks are easier if disentanglement has been achieved. So the three tasks are voice transformation, linguistic code switching, and privacy content masking. The benefits to having a multilingual model are that the phone representations can be learned together in a shared abstract space. And this can facilitate multilingual speech processing for things like code switching and cross-language voice conversion and things like that. Also to be able to create multilingual models from relatively small amounts of data. So this is the architecture. This was published earlier in the year in ICASP. This is the architecture that we used. This is essentially an autoencoder where the input is a waveform. The input is passed to two different encoders, two separate encoders, a speaker encoder and a phone encoder. And that information gets clustered in a VQ space. And finally, the speech is decoded with a wave RNN and it produces a synthesized waveform. So for speaker features, these are a temporal average pooling, and those are passed to the wave RNN as global features. And for the phone representations, these are passed in as local conditioning to the wave RNN. And then we've used, of course, these auxiliary classifiers to help encourage the disentanglement between speaker information and phone information. New in this work is that we also added a one-hot language vector as global conditioning to facilitate the multilingual processing. And here is an overview of the loss function on the bottom here. So there's a loss for the reconstruction on the decoder. There's also a loss for the phone representations, and that is the VQ clustering as well as the encoder. There's another loss for the speaker information, and that is the VQ clustering plus the speaker encoder. And then finally, there's the auxiliary classifier losses for the speaker classifier for speaker encoder and the adversarial speaker classifier for the phone encoder. So this is the architecture that we use, but I will talk actually about the evaluation of how it performs in these multilingual tasks. So the data that we used was the Swiss data, and this consists of 36 bilingual and trilingual speakers. So Swiss not being like Swiss, the language, but Swiss is how we pronounce that. So there's actually 4 languages in this data, English, French, German, and Italian. And you can see it's actually quite a small data set. So by the time we have gotten the balanced split for the held out data set, there's really only about 4 or 5 speakers per language. And in part because Italian only had 3 speakers in our held out set, we actually didn't include that fully in the evaluation. So this is a very small data set. The training strategy to get the original architecture into a multilingual model is as follows. First, we took the original BQVAE from Aaron Vandenoord 2018, and we trained that on VCTK data, that's multi-speaker English data. We trained that to 800,000 steps and used it as a warm-up model to train the dual encoder VQ model from Williams et al. 2021. And we trained that again on VCTK English multi-speaker data to 500,000 steps. And then we use that as a warm-up model to train the multilingual model, and that's this paper. We trained that to an additional 500,000 steps using this 4-language Swiss data. So the idea for the evaluation I'm going to present here is basically using BQVAE in an analysis synthesis paradigm. So in this case, input speech is passed into a trained BQVAE model, and the output is 2 different vectors, one being a phone VQ representation and the other being a speaker VQ representation. And then for synthesis, the 2 different representations are passed to the trained decoder, in this case, wave RNN, and the output is speech. So I'll use this analysis synthesis to talk about the different evaluations that we did. Each of the evaluations were evaluated with listening tests, and the surveys were administered with Qualtrics, and participants were recruited with Prolific, and they were paid $7.50 an hour. The listeners were filtered by their fluent languages. So we had people who self-identified as French fluency working on our French tasks, and people who self-identified as a German speaker fluent in German worked on our German task. Each of the listening tests had 20 participants. However, the number of speech samples evaluated in each task was very small, so 5 to 10 utterances on average. This was due in part to the held out set being very small, so in most cases 4 speakers per language. And also just the whole idea here is that these tasks are for proof of concept or toy problem. This is not intended to be a full-blown evaluation, but more to examine what this BQVAE model is capable of and to see if there's further lines of inquiry. So the first task was voice transformation. In this case, we did step 1, which is to get the VQ codes, and we ran analysis by providing input speech and obtaining the phone and speaker VQ codes. Next, we simply changed the speaker code. So if it was 109 before, we then changed it to 215. Those numbers are based on the trained code books. And the output would be speech sounding like a different speaker. We also performed voice mixing. So this is where we mix VQ vectors, and we did this in an element-wise average between 2 or more VQ vectors, sort of like a centroid, and then use that vector as input to the wave RNN as global conditioning, and then the output speech was in a new speaker, ideally a mix between both of the intended VQ vectors. And so here's the evaluation. We measured, first off, the percentage of listeners who indicated that the speaker sounded similar when they were presented with speech in their language and a given VQ code. And then we also measured the naturalness of the speech based on each VQ code and per language. So we found that the German and French have a higher speaker similarity than English. This makes sense because of the data imbalance. The speaker similarity trends hold across all 3 languages. The German MAUS naturalness was rated the highest, and that's highlighted here on the bottom. And on average, each of the VQ codes resulted in similar naturalness on average. So we would say that VQ code mixing is difficult, but possible. And then let me just play a few samples here for you. So this is English VCTK.
Sicher skip these things into 3 red bags, and we'll go meet her Wednesday at the train station.
So that's 1 VQ code. Here's another VQ code.
Sicher skip these things into 3 red bags, and we'll go meet her Wednesday at the train station.
And then this is the average of the 2.
Sicher skip these things into 3 red bags, and we'll go meet her Wednesday at the train station.
Okay, and then here is the English, French, and Italian converted into code 85. So here's the natural speakers.
The question as to why it was left out has not been answered to date.
And here's French.
Pour la grande sororité femelle fondée sur le culte du mâle, on repassera un Armel.
And Italian.
Perché aspettare l'arrivo dell'euro quando si possono ancora far soldi sui titoli in marchi?
Each of those utterances were then converted into code 85, so they should sound like the same speaker.
The question as to why it was left out has not been answered to date.
Pour la grande sororité femelle fondée sur le culte du mâle, on repassera un Armel. Perché aspettare l'arrivo dell'euro quando si possono ancora far soldi sui titoli in marchi?
Okay, so for the next task, we did linguistic code switching. So to perform linguistic code switching, we did this in the VQ code space. First, we ran analysis on English and, for example, French, and obtained the phone VQ sequences. And then what we did is we simply concatenated the phone VQ sequences for each phrase together and passed those into the wave RNN decoder, keeping the speaker identity the same. This worked out really well because the data set that we used had speakers who were naturally bilingual or trilingual, so we were able to keep the speaker identity constant. And then the output speech would be an English phrase followed by a French phrase. And we'll listen to some examples in a second. So for linguistic code switching, when we did the evaluation, we looked at speaker similarity. So how consistent is a speaker within an utterance? And we call that inter-utterance similarity. And then AB, this is a question to the listeners, is the speaker the same between synthetic and natural? Where synthetic is what I just showed you, where we concatenated VQ phone codes, and natural is where we've actually concatenated the original audio. And so we're reflecting here a percentage of the responses that indicated that yes, the speaker is the same between synthetic and natural. Finally, the inter-utterance similarity is the speaker identity consistent throughout the utterance. And we can hear sometimes it sounds like it changes a little bit. So we're trying to measure, can the decoder, can the wave RNN handle this code switching while keeping the speaker identity constant? And so let's listen to some examples here. This is German English.
Freilich beginnen die Ausscheidungskämpfe schon jetzt. Vacancy wants to sell its remaining state.
And this is English French.
Every year we have the same problem. Les gens sont encore au stade des entraînements.
Okay, so the French English here is possibly degraded, the intelligibility because of the language imbalance. So French is more frequent in the training data and English is not. We also think it might be more difficult for the decoder to recover from the code switching, which is why the second language usually sounds worse than the first in the code switch. Finally, the English and French might use different code distributions, and so that can be contributing to the lower quality. In the third task, this is privacy content masking. And so what we're trying to do here is use the VQ code sequence to target specific content that we want to mask. And so once again, we run analysis with a VQ-VAE model to obtain the VQ code sequence. In step 2, we choose positions within the code sequence that are time aligned to the content words we want to mask. So in this example, we have position 1 to mask the phrase "these things," or we could choose position 2 where we mask the phrase "3 red bags." And so we also explore the 2 positions, beginning of the utterance and end of the utterance, as well as 2 types of masking. One is to simply reverse the VQ code sequence, which should reverse the speech in the middle of the utterance. And then we also tried using speech shape noise. And I'll play an example of speech shape noise right here. Okay, so that sounds essentially like wind. When we add the speaker VQ code and synthesize the speech shape noise with a speaker VQ code, it sounds more like mumbling. Okay, so that's hard to hear. It's very low volume. Okay, but you get the idea. So finally, step 3 is to go ahead and apply these masks in the VQ code space to try to hide the content of the VQ sequence, and then run synthesis, and the output is then speech that has this targeted area of the content masked. In this evaluation, we asked the listeners 3 questions. So one is to find out how the speaker has changed throughout the utterance. So is the speaker voice consistent throughout the utterance? And our speaker similarity question, and we reflect the percentage of participants who answered yes. In the second question, we use an ASR-based word error rate to see, does a particular type of masking or masking position degrade the ASR capability? And we also have the natural speech without masking word error rate for reference. And in the third question, we did an A/B mask preference test just to see if people tend to prefer reversal masking over the speech shape noise. We found there was a slight preference for the speech shape noise over the reversal. So what we also found is that the masking at the beginning of an utterance is more difficult for ASR, and that the speaker is more consistent when the masking is at the end of the utterance. So what this suggests is that the decoder does have some trouble recovering from a masking, but also with a speech shape noise, it tends to recover better with speech shape noise than with the reversal. And I'll play for you an example here.
Spoons of fresh snow peas. 5 thick slabs of hoo-ha-ha and maybe a snack there by the box.
5 thick slabs of hoo-ha-ha-ha is what she said. And then here it is again as a reversal mask.
Spoons of fresh snow peas. 5 thick slabs of clean food and maybe a snack there by the box.
So in this case, she said 5 thick slabs of blah, blah, blah. It's hard to tell because it's reversed, the speech is reversed. So the target phrase has been reversed. So that was the third task. And so finally, the findings of our paper are, we can adapt a monolingual model to a small amount of multilingual data. It is possible to mix VQ codes to create new voices, although I would say this needs quite a bit more work to get it running like at scale. But as a toy problem, we show it does work, it can be done. It's also possible to do voice transformation across languages. So using a speaker who we only have data for in German, and then trying to transform their voice into something in French, that is possible. And that the VQ space that was learned in this model is a shared phone VQ space between all of the languages. We also know that the decoder can handle code switch speech, which is nice to know. But there is some further investigation. So one is to explore the limits of code switching. So I showed some examples of very simple code switching, which is not really how people do it in real life. So what we would want to know is the quantity and the duration of the switches. Does a decoder handle a very fine-grained duration of switches? We also want to analyze the VQ codebook, so to understand a little bit better about the disentanglement and which types of phones are shared. Finally, there's more room for investigation about this content masking for privacy using VQVAE, and to see if this method can preserve the speaker information or be improved for ASR capabilities. I also have a page of samples and code. So that's all I have.
Thank you very much, Jennifer. As before, I'll start with some questions from the chat, and then we'll switch to the room, see if you have any questions there. So I'll read them out for the benefit of people streaming on YouTube. I think they don't see the questions. So I think Alexis is asking about task 2, the code switching task, where you're considering consistency of speaker similarities. He's suggesting, I think, a sort of a reference or control group of English to English, or French to French, because you might not get 100% then. Have you considered setting the upper bound in that way?
Yes, so we have explored that more recently, just basically concatenating entire files together to see how long an utterance can we synthesize with wave RNN in a single language. And what we found is it can actually get quite long. So if we stay in one language like English or French, for example, we can concatenate about, I think, 25 or more seconds of speech, and the wave RNN does not break. But that's not reflected in this paper. That was additional work that we did after, more recently.
Adriana asks, could you sort of suggest a practical application for the privacy masking? She's suggesting if you knew the phonetic content, which I guess you don't, you just have audio, but you do know where to mask, would there not be sort of simpler ways of masking? So I guess the first part is the most interesting. Actually, what's the application of privacy?
Yeah, so the application for that, actually, so if you look at some of the speech privacy research, it's usually focused on things like removing information about the speaker. So taking away their gender, their identity, their age, things like that. Whereas there's not been as much work in looking at the content. So there are like, there's been some research that looks at trying to create a device. You could actually set a device in a room. It looks at the room characteristics, like measures the impulse response and stuff like that. And then it adjusts to the room, and then it emits a signal that makes a speech within that room hidden to anyone who might be like right outside that room if the walls are thin. For example, in a doctor's office or a financial institution like a bank, or other places where you might need high security and have private conversations. So with content masking, what we're trying to look at here is a way to have a capability that can target specific words. So if you had some kind of a named entity recognition, you could be monitoring and listening for specific information like bank account numbers or special locations or names of people, and then mask that in somewhat real time.
I'll switch to ask if anyone in the room has any questions. Step up. Yep, here comes somebody. Too small to identify. Yep.
Hey, thanks. I was just wondering if there's why do you use VQ codes for the speaker embedding rather than just say an embedding table?
Yeah, so the original VQVAE, what we found in our ICAST paper, so going back to some previous work, was that it doesn't generalize well to unseen speakers. And so there will always be this limit on how you can represent speakers because they're using like a one-hot embedding or things like that. So the idea here is that we've incorporated a learned speaker embedding with the VQVAE. There are, of course, other ways that this could be done. We didn't find that any of the ones we tried worked except for this one. And so this is a semi-supervised paradigm. We also tried a fully self-supervised paradigm where the speaker information is simply the global temporal average pooling. So it's a global feature, but there's nothing necessarily speakerish about it. Yeah, so I think the generalizability is my answer to that.
I think that kind of probably handles Dan's question in the chat about why you just didn't use a pre-trained speaker embedder. I'm going to take questions slightly out of order so we get them from more different people. Rob Clark asks about just bilingual natural speech. People don't necessarily sound like themselves across two languages, although there are papers that show that they basically do. He's suggesting they might have different pitch ranges in their different language. Does that affect the way your model's trained?
Yeah, so it's interesting you mentioned this, Rob, because right now we have an MSc student here at Edinburgh working on more in depth on the code switching and the voice conversion. And one of the things that she's looking at, that she's observed, is that our bilingual data tends to have something carried over when we do code switching. It's almost, we've been calling it like an accent, but this might actually be what it is. It's a pitch range, perhaps, so it might be something we look at a little further. That project is about to come to an end, so I don't know if we'll get to it, but it's a very important question, yeah.
Yep. Anyone from the room should just step up and I will see you on the video, but in the meantime, I'll go back to some in the chat. Adriana again asked the question, I think a common question that is going to be hard to answer. Did you explore the VQ space of the phones and is it interpretable? Is there any clustering? Does it go by language? Is it shared? All of those questions.
Yeah. So I'm actually working on this analysis of the VQ codebooks right now. So I hopefully will have something to share with the community officially soon. But what I can tell you is that we've looked at the distribution, and what we find is that similar languages, these are very related languages: English, French, German, and Italian. So it's not too much of a surprise to know that the distribution of codes, actually the range of codes is the same or similar across these 4 languages, but that the quantities and the distribution changes a little bit on a per language basis. So what would be a very frequent code in English is a very infrequent code in Italian, for example, but they're still used, they're still utilized. It's also possible that there's just some redundancy in there. So maybe removing that redundancy might reveal better how that clustering space is being used.
Great. Well, we're staying greatly on time, so I'm going to stop the questions there and we can take it into the discussion session at the end. Thank you very much, Jennifer.
Thank you.
And invite the next speaker, Xin Wang, to reveal himself. And while I introduce the next paper, we're continuing the NII theme. The paper presented by the second author, and the paper is entitled Text-to-Speech Synthesis Techniques for MIDI to Audio Synthesis.
Yes, thanks, Samuel. Just to test again, can you hear the sound?
Yep, I can hear that.
Okay, good. Good. Start. So hello everyone. So this is a joint work with Erica Cooper and Junichi Yamagishi at NII. I'm a second author. In this work, we apply the TTS methods for MIDI to music audio synthesis. It's a preliminary work, so there will be extension in the future. The motivation for this work is that when we read the papers, we notice there are many similar topics across the 2 domains, the transcription, the language modeling, the voice and timbre conversion. But for this work, we're considering whether we can use some of the TTS models to convert the MIDI input into the music audio waveforms. This is motivation. There are many frameworks we can use for both tasks. For this work, we use the statistical parametric speed synthesis. So as you can see, we have acoustic model to convert the input to the acoustic features and the waveform to produce waveform. But of course, you can also notice some difference. I think the first difference I'd like to emphasize is that for the MIDI to audio synthesis, the pitch is really crucial. If the pitch is not is out of tune, then it's going to be rubbish. So pitch is very important for this task. And another difference is, of course, is on the input. So for this task, our input is the music score or any kinds of format that is compatible with the MIDI specification. So we will use the MIDI API to convert the music score into the MIDI piano roll representation. So this MIDI piano roll basically specifies at which time we should hit which key and how long we should keep it. Although it's called piano roll, but it can be used for many other instruments. So this will be the input to the acoustic model. To give you a more concrete example, we can compare the input future vectors to the acoustic model at one input time step. So for the TTS case, we may the input vector may encode the phoneme ID or syllable ID, while for the piano roll, as you can see, it's basically a multi-hot vector where each dimension specify whether we hit this key or not, and how strong we hit this key. So this is named as the velocity. So this will be the input to the acoustic models. Besides the input on the input, besides the difference on the input features, we can also notice here we have two options for the MIDI piano roll representation. So one has the same length as acoustic features, another one has a different length. So these two types of input actually corresponding to two applications. So in the first application, which we call silent instrument, is the application where the users want the system to produce exactly what the input MIDI has specified. So the acoustic features should be aligned with the input. So the duration information is fully given for this case. But also there is another case where the user might want the system to add some professional expression into the MIDI representation. So it might change slightly the duration of this key and do something like this. So in this case, the input and output of the acoustic model is not well aligned. For this initial work, we focus on the first task. So the input and output is well aligned. So it's easy, and based on this work, we will go to the second task in the future work. So that's the task. So giving this background information, we can know, so in this work, we are going to ask whether we can use some of the TTS components for this MIDI to music audio synthesis. So what kind of models, what kind of acoustic models and the waveform model we use? The first one is the Toctron. It's widely used in TTS, although it is not necessary for this task, but we still use it because we want to test this performance and prepare for the next task. So this Toctron is based on our previous work, which is slightly different from the original Toctron. For this work, we used a few variants of this Toctron model. The first one is simply change, just downsampling the input and output features. Second one is slightly different, where we fit the input piano roll to the prenet. By doing so, we hope this information can guide the attention block in the decoder to learn the attention from the input to the output. The next variant is really for ablation test, where we move the downsampling and the additional input to the prenet. So those will be the variants which we will compare in the experiments. In addition to the TTS model, we also include one model from the music field. It's called performance net. As you can see from this picture, this performance net is straightforward. It simply converts the input sequence of features into the output, and the input and output is well aligned. This is widely used. I think it's somehow widely used in the music field to convert the piano roll into the audio waveform. So we include it as the reference model. These are the two options for the acoustic models. About the acoustic features, we have two choices. The first one is the mere spectrogram. The second one is a MIDI filter bank spectrogram. This feature is very similar to the mere spectrogram. The difference is the filter bank. So as you can see from this picture, we design we built. We'll have one filter bank. We have one filter for each MIDI index, and the location of the filter is decided by the frequency of that MIDI index. So this is straightforward. Here I show two examples of the output from these two feature extractors. As you can see, the MIDI filter bank spectrum features focus more on the low frequency band. The reason why we use this MIDI filter bank spectrogram is that if we compare the input piano roll with the MIDI filter bank feature, we can notice the relationship or the mapping from the piano roll to the MIDI filter bank would be easier than that from the piano roll to the mere spectrogram. So by using this kind of features, we hope the acoustic model can be well-trained, can be better trained. So these are the acoustic features. For the waveform model, it's based on our previous work, the neural source filter waveform model, but it's slightly adapted for the music task. So there is an excitation signal, which can be either the sine waveform or the noise. So I will explain the details on this excitation signal later in the experience part. So these are all the components we need to build these models in our experiments. So let's go to the experiments. For the experiments, we use the Maestro version 2 database. So this is a high quality piano database. And one important thing about this database is that the MIDI is recorded when the pianist play the piano. So there is a well-aligned audio and the MIDI input and also piano roll. So this is perfect for this task. For the data, for the training, development, and test set, we follow the official recipe. So as you can see from this table, and we build the models using 24K kilohertz waveform. For the models, we compared the models in this list. There are so many models, but let me go one by one. The first two models are software wells, commercial software wells. One based on the sample-based approach. Another one is the physical model-based approach. Another reference model is the original performance net, which used Griffin-Lim to convert the output of the acoustic model into the waveform. So we use the official source code. For the other for other models in this experiment, we divide them into two groups. The first one is copy synthesis. So in this case, we fit the natural acoustic features to the NSM model. So as I mentioned, there are we need the excitation model. We need the excitation signal to the NSM model. So two choices: either the sine waveform from the MIDI or completely random noise. The second group, so we simply build pipelines where we change, we use the Toctron or the performance net as acoustic model, and also the different variants of the NSM model to produce a waveform. So these are the experiment models. This box plot shows the listening test results. It's a large scale listening test where we hired more than 200 non-professional participants. There are many messages we can read, but let me first just compare the natural sound and the two from the software wells. So as you can see, the physical model-based approach actually is rated slightly higher than the natural sound, although the difference is not significant. If we further compare the copy synthesis system, we can notice the two of the well-performed copy synthesis system can actually achieve quite high quality. So I would just play some samples. So as you may perceive from these samples, although the physical model and the sample-based model rated quite high, but we can perceive there is no room reverberation in those soft wells. But this kind of reverberation can be well captured by the neural waveform model, and it works quite well in this copy synthesis condition. However, when we go to the pipeline, as shown here, so we can see there is degradation in terms of the synthesized quality, no matter which variants of the Toctron system, Toctron model we used. So I'll just play one sample from one of the systems. So I think you may hear the muffled sound and also the blurred low key sound in this generous audio. So I think that will be the artifact caused by the acoustic model. There are more models we can compare, for example, the Toctron system and the performance net, although the difference is not really significant. But however, if we compute the pitch distortion or the degree of out of tune, we can notice the Toctron-based system are slightly better than those baseline models, the performance net-based models. So from this figure, we can notice there is some advantage of using the Toctron variants as the acoustic models. So that's all the message from the experiments. To quickly wrap up, so in this work, we apply some of the TTS components to MIDI to music audio synthesis. And many components can be shared also, not only from TTS, I think also from words conversion field. Also the performance bottleneck may be on the acoustic model and also waveform models. For the waveform models, although the physics and sample-based models can work quite well, but they are not trainable. So they cannot capture the characteristics in the natural sound. But this can be done using the neural waveform model. On the acoustic model, our experiments, actually, Erica have more experiments on this. It's hard to learn good alignment for longer input because the music input is quite long. This will be quite challenging if we switch from this simple task to the task where we want to learn the AI performer, which can change the duration of the key. So this will be an interesting topic, and we'd like to explore in the future. So that's the end of this presentation, and you can find the codes and also the samples from our website. Thank you.
Thank you very much for the presentation. As is now traditional, I'll start with the questions in the chat. Sebastian asks about your listeners. What do you know about their musical backgrounds? And if you know anything, does it make any difference to how you interpret the results from the listeners?
Yes, good question. In this case, we hired the evaluators on a crowdsourcing platform. We don't require them to be professional. And according to the ankit, I think most of them are not actually professional musician. So, but based on this configuration, I think the evaluators focus mainly on the quality of the sound. So that's why we can hear the quality from the full pipeline is quite much lower compared with the copy synthesis case. However, as you suggest, maybe in the future we will recruit professional musicians to rate not only the quality but also whether the sound is out of tune. I think it will be one important topic for the next stage. But of course, it will cost more money for that.
Yep, Javier asks, he thought he heard in the tachytron making sort of mistakes in the playing. I guess that's mistakes that were perhaps there, not there or were there in the MIDI input. So can tachytron make mistakes with respect to its input, I guess.
Yeah, so in this case, first, by saying mistakes, I mean, to my mind, there's two types of mistakes. One is we have perfect input, but the Tactron system cannot render it as output. Another one is we have input in the input MIDI, but we would like to see whether the Tactron system can correct them. So for this work, because the task is simple, to convert the well-aligned input into the output. So I guess most of the mistakes happen in the rendering part. So giving the perfect input, the Tactron model cannot actually deliver or produce good spectrum features. Also, I'd like to mention that the input piano roll in this case are perfect. So if you hear the mistakes, then it must be the outcome from the acoustic model.
Yeah, again, people from the room should just step forward so I can see, otherwise we'll keep on in the chat. So I'm going to actually combine Rob's question with one I had. Rob asked whether he thinks the tachytron quality loss is just because the spectra are smooth because of these independence assumptions. That kind of follows from my question, is why you chose to go for piano, which is a polyphonic instrument, with tachytron, which is designed for speech, which is not polyphonic. It's a monophonic. It plays one note at a time. Why didn't you try something monophonic?
Thanks for the question. I think the motivation is simply, just as you mentioned, to ask whether it can work in this case. That's the first answer. Second answer is that we choose the piano in this case because of the database. So not all the database has high quality audio and also well-aligned input and output. So that's the for practical reason we choose this database, which only has piano sound. But by the way, we also our institute also records one new database where we have multiple instruments. In that case, monophonic with well-aligned MIDI, and we would like to see whether the pipeline still works on in those cases.
Yeah, we have time for another question if there's one in the room or anyone on the chat. I'll throw in my kind of one sort of very high level question is, I mean, why do people think these neural models are worth doing at all, especially for piano, where kind of physical modeling synthesis is incredibly good?
Yes.
It sounds astonishing, and you can make any piano you want.
Yeah.
Why would you do expensive trainable neural?
But I think first, from the copy synthesized samples, you can also probably perceive how the physical model might not capture all the acoustic characteristics in the natural sound, for example, the room reverberation. So we can guess, okay, we can add these components through additional components to the physical model, but it needs tuning and it needs engineering. So I guess one reason is to use the data-driven approach to learn this kind of characteristics, which cannot be easily wired in the physical model. Another one is for the AI performer, which where we want to change somehow the duration of the key to add additional expression to the input MIDI. So that cannot be easily done using the traditional physical model or non-trainable models. So that would be the answers.
Yep. And I think we have a question from the room. Is that Gerard at the front?
Yeah. Hi.
Hi.
In fact, I suspect that you use the tachytron, in fact, to put these notes in context and to somehow learn the structure of a partition. So, do you have any hints about the capability of the structuring capability of the syntactic, in fact, organization of a sound that provides, in fact, the tachytron encoder? So perhaps the quality is bad, okay, but perhaps the structuring, in fact, the way the partition is organized, not only a succession of notes, but organized in it's a music score. So do you have any hints or any project in examining, in fact, the structure that the structuring of sound that the tachotron is providing?
Thanks for the suggestion. That would be definitely
more science than technology.
Yes, that would be the definitely ultimate goal of this research. But currently, we are struggling with the attention part, which cannot well learn the input from the output, the alignment. So after we, I think after we solve this problem, we can analyze what kind of attention map we can learn in the encoder. Especially in our tachotron system, we have additional self-attention, which is supposed to be capable of learning this kind of high-level structure. But by this time, we don't have answers to this question yet. But we will definitely do that in the future.
Great. Thank you again for that presentation. We're going to move on now. Any other questions, please take them into the discussion session later. I'm going to thank you again, Chin, and invite our next presenter to unmute. And our next paper, I think, continuing the NII theme, and you'll forgive me if I pronounce your name incorrectly, it's Huybrechts, whose paper is a preliminary study using vector quantization latent spaces for TTS voice conversion systems with consistent performance. Please go ahead.
So, hello. Can you hear me?
Yes, it's good.
Okay, thank you. My name is Lung Hyuthi from National Institute of Informatics, Japan. So I will present our work on using vector quantization latent space for text-to-speech and voice conversion system. So the motivation for this work is that in speech synthesis research and development, usually people focus on the end product. With a natural and aggressive synthesized speech with a makes sense because that's what we want, right? But at the current state, we have very high and reliable synthesized speech. So the motivation of this work is that if we focus on the latent representation with a specific trace, we open up possibility to use these application using this system on many different applications and scenario. Specifically in this work, we focus on the discrete latent feature compared with a continuous one. So, in this work, we will investigate the use of vector quantization variation of autoencoder, a component to model a linguistic latent space of our unified text-to-speech voice conversion voice learning system. We call it non-autoregressive system. So besides the general evaluation on the subjective quality and similarity, we also want to show how a carefully designed system can be used to investigate the latent space with a starting point for further research on the topic. First, I want to introduce our system. So just to be clear, so we report the non-autoregressive system in our research publication. Anyone interested might want to check our journal paper on this. For this specific paper, the focus is the novel part is that we change the latent linguistic embedding using a vector quantization component. But I will go to the structure of our voice learning system. So we in the left side here, you can see it has lots of separate modules, but it's actually not that complicated. If you look at the right side, you can see that we have a text-to-speech with a very typical multi-speaker text-to-speech system. If you think about it, we have a system that converts that directly to waveform. So next to it is a many-to-many voice conversion system. You can see that we basically convert a waveform to another waveform, but we change some kind of speaker identity right here. But our system is a combination of the two systems into the one in the left side. You can see here the text encoder, speak encoder, speak decoder, and neuron vocoder, which is represented in a very abstract way because it actually doesn't matter what kind of network structure you're using. Obviously, it will affect the performance, but it does not affect the general methodology. So I mentioned earlier in our original journal paper, we're using a VAE pay encoder to model the linguistic space, and a novel part of this particular paper is that we're using a VAE pay encoder, VQ-VAE pay, sorry. So because the chain of the component using to model the linguistic latent space, we also had to change the way we're training the initial model. So for our model, we train on the module together by optimizing one specific designated log function. Even though it could look complicated, if you look at this one and this one, it has a very typical VQ-VAE training structure with the text encoder handle the text input, while the speak encoder handle the speak input. The specific thing about our proposal is the way that we try to enforce a certain consistency between the text and speak encoder using this function. So it also takes on the very similar structure of VQ-VAE system. So we call this kind of system a multimodal network, but what we really want is that we train a system with interchangeable encoder modules. And so that it could be used, but we could use either the text encoder or the speak encoder, or sometimes we want to use both at the same time. So after the supervised training, initial training, we can move on to the voice learning step. What is exactly voice learning? So depend on the people you asking, they will have different definition for that. But in our case, we define voice learning very simple. We want to get the individuality of a certain speaker, or basically want to learn their voice, and then generating speak from that voice. The interface that we're using to generate speak of the learned voice is not important. So it could be text to speak, it could be voice conversion, or any kind of speech synthesis system, as long as we care about the particular voice that we synthesize. So that's how we define what voice learning means in our research. So for the voice learning step, we had to more step in that. So in the left side, by using the speak encoder and speak decoder, we can fine tuning this one using only speak. So we didn't need the transcript of particular data of the particular target speaker. So we can, so we can adapt the speak encoder and the neuron vocoder independently, and because there are no text involved in this step. And the second more step, because many work report us by adapting or fine tuning these modules separately, it might not be the best solution. So some of them propose that we should tuning them together. So that's why we have a second step. But the second step is totally optional. So after the voice learning step, we basically have a system that could generate speak with the target voice, either by using it as a text to speak or a voice conversion system. And we didn't need the test of that particular target speaker. So that's the the function of this particular system that we report in previous one, and for this paper. So we move on to the specific one for this paper. It asks we want to have a VQVAE by linguistic latent feature. So what exactly that mean? So first, we want to talking about consistency. So what exactly consistency mean? So if we think of that and speak a alternative representation of linguistic or realize different kind of realization of linguistic, then consistency between the text encoder and speak encoder, it has given the same content of text and speak, we will obtain the identical linguistic sequence by transform them using our text and speak encoder. So how can we do that? So in a training step, we enforce a certain consistency between the linguistic space and the text encoded space and the speak encoded space by make sure that the same content will stay low together. We can do that in a standard way. We didn't assume anything about the latent linguistic space. But the problem with that approach is that it's simple. That's actually a good thing, not a problem. But the problem is that and speak is not a one-to-one relation. What I mean that's given the same speaker, if you ask them to read a sentence multiple times, you will have multiple realization of that text. In a similar way to think about it. So in our journal paper, we are both using a VAE-based encoder. We assume that the linguistic latent space had this variational like traits or property. So basically, we training the speak decoder in a denoising fashion, and then we can bind or tying them in a density-wide function. But it also has on the weaknesses of a VAE-based system. There are lots of paper on that, especially for like image size instead of speak. So in this particular paper, we are both using a VQVAE-based structure to model this linguistic latent space. So the first thing we can see that we basically list this latent space into multiple bin of linguistic latent embedding. So the point of all of this is that we want to train a highly consistent and interchangeable text encoder and speak encoder, and that is the reason we enforce on kind of policy on the training step. So I just explained the pipeline of our voice learning system that could be used for both text to speak and voice conversion. So I quickly go into how we set up the experiment in this particular paper. So we test our idea on Japanese data for this particular experiment, but in our reverse paper, we do it that on English. So if you're interested in English, you can look into our previous publication. And in each training step, we will train on the module together in a supervised way. What supervised means is that we need both test and speak up a lot of speaker and a lot of data. So in a voice learning step, basically our task that we want to learn voice of a new speaker. We only use speak of the speaker. Specifically, we do two separate evaluation in the duration of the first task. We adapt using around 50 minutes of speak from a couple of female Japanese Turkish speaker. And for the second one, we using just one speaker, but we train the amount of adaptation data and compare it with a supervised baseline with a lot of translated speak data. So for the evaluation, we just want to add, we just want to know that the new system and the old one, how the performance comparison between the news and our one. So the question is very simple. Which of the sample region is better in quality, or which one is more similar to the target speaker? And you can see that the new system is worse than the old one in almost on measure, but the difference is not that much. So basically, we want to say that the new system can be used for voice learning, but the performance is raised a little bit compared with the old one. For the second experiment, we want to see how the different amount of data will change the performance. So one interesting we found is that for our particular voice learning system, more data mean better performance we expected. But then if we continue to add more data, the performance kind of decrease for both the old and the new system. So that is something we need to working on in the future work. Compare with a supervised baseline, our system is not comparable because we have different amount of data in the learning state. So conclusion for the experiment is that the performance of the VQ VAE by is not as good as the old one, but it still has a certain quality in that. So why we even care about VQ VAE if the performance is not as good as the old one or the continuous one? One thing it does tend to it like discrete trade up the latent space. We can look at analyze the result in a couple of ways to get insight of what actually going on. So given the silent font on the side, for the text input, if we get a silent font, we can see that two different vector is generated when we're using a text encoder. So just to show you that the text encoder is color like orange. The speak encoded L is orange, the low one is text encoded. And when these two overlap, then we have color black here. So you can see that for the particular silent font, we have a couple of different vector instead of just one, right? So the input is silent font, but depend on the location, we have different vectors generated by the text encoder. For the speak encoder, given a silent segment of speak, we have a lot of different vectors generated here. We actually expected, because even though we say that this segment of speak of utterance is silent, it's not really silent. It could be there's some noise there. We just want to say that the whole thing is silent. So it's not unexpected, but it's a nice thing to see. So, and for this particular utterance here, we can see that the overlap is around 50%. So the conclusion here is that even though we apply on kind of policy to enforce consistency, we didn't actually achieve that in this particular experiment, but we got to 50%. So that's something, right? Another way to look at the
I'm just going to ask you to try and wrap up. We're running quite a long time over just now.
Okay, sorry. So another way to look at it is look at the histogram of the vector quantization. So you can see there's still mismatch between two. For the silent font particular, you can see that there are two main vector and a couple of other histogram here for particular font name. So a reminder is that the training data is Japanese. So conclusion. So why we even try to doing a unified text to speak and voice conversion system? Because it's convenient to have one thing to do both, right? And it was certified that it could be used for learning new voices using speak without text. Moreover, specifically for this paper, by Viacheslav that using into parallel modes, we basically rely a way to inspect the hidden feature. If we can observe something, then we might utilize this observation, right? Somehow, but that is for future work. So why even use discrete latent linguistic embedding? So for very specific application, you will want that kind of property. But for this particular paper, it is useful to analyze the latent space compared with a continuous one. So in summary, a VQV-based encoder can be used for our voice learning system with minimal adjustment with acceptable performance and allow more iterative analysis on linguistic latent base. So thank you for your attention.
Thank you. We'll try and squeeze a few questions in if we have any, either from the room or in the chat. I'll start with the first one in the chat, which is from Dan. Dan asks, for voice conversion, did you consider also including an F0 sequence to help with prosody reconstruction?
I think if we had that, it certainly improve the performance, but I'm not particularly interested in improve the performance in this work, just analyze the latent linguistic base. So I didn't do that, but I think, yeah, if you do that, it certainly will improve the performance. So.
If we have any questions in the room, as usual, just step forward so I see you. Yep, we have a question from the room. Shah.
So it's very clear, in fact, that you explore, in fact, your latent space using vector quantization. There are perhaps more interesting ways to directly, in fact, probe your latent space using latent space analysis, or nobody is working on the analysis of this latent space. We don't know it's a mind view, your slide of 7. You don't know how the phonemes and so on are distributed over the latent space. So it could be interesting to first examine the structure of the latent space, and after to be able to use the model to JMM or vector quantization, which is appropriate, in fact, to the space you are dealing with. Afterwards, it just is too late. No, what is your opinion? For example, so you imagine that you will cope, for example, with F0, with intonation. It would be interesting to know what is the latent space of the intonation. To be able to understand, is it continuous, discrete, how many different categories they are, and so on. So I think it's too technological. You have to. We don't learn. We have you have nice statistical tool to, in fact, to compress corpora, but at the end we don't learn anything.
Yes, for current work, we didn't have a lot of insight or analysis on what exactly we have or what exactly we want to do. But because we have both a text-to-speech and vocal version in the same system, we basically can compare it in some way and have a very specific application. Even that if we can trust our latent space, right? Let's say that you have a speak utterance from a speaker that can speak with a perfect pronunciation, and a speaker speak the same utterance but with some certain accent, then we can compare them, right? And we can see the mismatch between the two. So,
but it could be interesting to know how your latent space is populated, in fact. So do you have conglomerates? Is that more continuous space? Are they so? You don't know how your space is populated.
So
processing guy, it's really completely. First, you have to analyze the problem, and after to find solution. Not find solution, and perhaps after discover the problem.
Yeah, that's a good synthesization for our current work. Yeah, but we certainly want to do more in the future, because the problem is we didn't have any specific like objective in this analyze. So it's difficult to say exactly what we see here. And basically it's just like an introduction or a preliminary study to show that the direction that we could do instead of like just see some kind of luster of like latent feature. Basically you can say that seeing the kind of luster figure doesn't make any sense either, because what does that mean that the point low together? What does that mean? So, but in our work, we at least had a comparison between like the test and the speak. So we had this phoneme and this is the speak and how they align with each other. So, but actually, it's a good synthesization because we didn't have a specific objective in the paper. So, yeah, I could understand your point of view. So, but hopefully, I could extend it work more in the future. So,
okay, thanks for all the questions. I'm going to draw a line under it there, keeping reasonably on time. Thanks very much for the presentation. And I'm going to invite the final presenter of this session, Patrick Lumban-Tobing, to unmute and start presenting for also continuing the Japanese theme, but I think we're moving down further south. And for the longest title of the session as well, I'll attempt it. It's a low latency, real-time, non-parallel voice conversion based on a cyclic variation autoencoder and multiband wave RNN with data-driven linear prediction. I'll say good luck fitting that into 15 minutes. Take it away, Patrick.
Thank you very much thank you for the introduction. Yeah, first I want to say thank you for giving us the chance to present our research. And in this presentation, we will show a real-time demonstration of voice conversion. And I will briefly read the title of this presentation with the converted voice.
Or the title of the presentation is the low latency, real-time, non-parallel voice conversion based on cyclic variable autoencoder and multiband wave RNN with data-driven linear prediction. I'm Patrick from Nagoya University, Japan, and I converted Platinum to my voice.
Then, yeah, so next I will explain the contents of the presentation. Yeah, so first I will briefly explain about the background and the motivation of this work. So basically, the voice conversion is basically it's a conversion of voice characteristics, and it can include several traits, like short-term traits. It's a spectral envelope traits, and long-term traits that includes the prosody. And of course, we also need to consider the fundamental frequency and the voicing from the glottal fold. But in this work, what we try to do is that we want to develop the online PC system, because we can obviously develop the offline PC and we can maximize the performance. And in order to develop the online PC system, there are a lot of things to be considered, and obviously we need to consider the trade-off of the performance and the machine that we used. And in this case, we try to develop this kind of system. And so the objective of this research is the LLRT, or low latency real-time PC, and we extended that we want to develop it with the more flexibility of the development process, such as we want to use non-parallel data and possibly without textual labeling, and possibly we want to preserve the performance while considering the usage of the low machine specification. To develop the VC, basically, there are a lot of works, of course. And in this work, we want to focus on non-parallel modeling. Of course, there are also several models, but in all of them, the common point is that in non-parallel VC, mostly we try to find a speaker-independent representation. So based on recognition and generation-based modeling. In this case, we have encoder and decoder, and we try to model the speech features, for example, spectral features or spectral envelope, and we try to find a common representation between speakers. Of course, we have phonetic posterogram, PPG, and then we can also use TTS, which mostly sequence-based modeling. But in this work, we try to do a low delay model for mostly frame-based system and to allow the low latency processing. And after we model the speech features, obviously we want to generate a waveform. Of course, if we want to improve to get better quality, we want to use neural vocoder. And in this work, we want to utilize the low latency real-time neural vocoder, LRTVC, and we want to combine it with non-parallel modeling and linguistically unsupervised modeling and the low latency spectral model. So these are basically the works that mostly related to our objective in this research. And in this work, what we try to do is that we try to use the VA-based spectral modeling, the partial autoencoder, where we can use non-parallel data and it can be developed without any text labeling. And then we want to utilize the frame-based model, and because so it's mostly low delay model, and then we just use the extracted features from STFP spectra because it's fast. It can be extracted fastly in a very efficient manner. And then we utilize the LLRT neural vocoder, which in recent works, it includes the use of the sparse model, sparse autoregressive model based on WaveRNN, and several techniques can be applied, for example, multiband or more additional techniques to improve the quality. And of course, if we use LLRT for spectral modeling, there will be trade-off, and we can actually improve this kind of modeling by doing fine-tuning, utilizing the waveform modeling from the neural vocoder. That's what we want to do in this work. Yeah, so I will just briefly explain about the cycle VA, the cyclic partial autoencoder, or the cycle VA-based spectral modeling. And basically, the cycle VA is it's improved version of the VA VC, and it tries to add more latent variable, speaker-dependent latent variable. Well, basically, we try to use the sampled converted features. It acts as additional speaker-dependent latent, and in this process, we can actually somehow obtain a cleaner speaker-independent latent space, the Z part. And in this case, what we can find is that we can find more similarity with the same content. So because if we have same contents, the latent speaker-independent latent should be the same, and we can improve the conversion accuracy. And in this work, what we try to do is we try to use mass spectrogram as features rather than spectral envelope, because it can be extracted more efficiently. And of course, we need to do more advanced modeling and to use these features because it's more complex, and including vocal tract and the harmonics features. And in this case, we use additional encoder to help the latent representations. And then we can also estimate intermediate like F0 or excitation features to help the decoder to generate the mass spectrogram. And then the optimization is performed with also with the Gaussian PDF. So in the end, what we do is we do sampling to alleviate the oversmoothing from the mass spectrogram. So that's the cycle VA model, cycle VA spectral model, and I will just briefly explain about the neural vocoder. And in this work, what we use is the multiband WaveRNN with data-driven linear prediction, or MWDLP. It uses the data-driven linear prediction for discrete waveform modeling, including also the STFT loss. And basically, this model can preserve the quality and can be used for multi-speaker data, and it also works on a band rate model. So this is the data-driven LPC, which are estimated from the network. And then because this network is a sparse model, we can use this kind of model for the spectral model, and then we leverage this optimization of the waveform to improve the spectral model. In the proposed system in our work here, what we use is the sparse modeling for the cycle VAE, as I've said before. And then this is basically the implementation where we used about 75% density of the encoders and the decoder with 512 GRE for the encoder and 640 GRE for the decoder. And in the cycle VAE and in the MWDLP neural vocoder, we use factorizations in the implementation to efficiently compute the matrix vector multiplication and so on. So obviously there will be trade-off, and as I've said about several times before, then that we want to leverage the waveform optimization to fine-tune the spectral modeling. So in this work, we just basically pre-train the models, cycle VAE and the MWDLP, and then what we do is we fix the MWDLP and then the neural vocoder part, and then we discard actually the decoder excitation. Then we retrain all of the modules of the cycle VAE, and finally we fix the encoders and fine-tune the decoder. So this is the final model that we can get, and from our investigation, it improves the performance compared to the basic LRT system. So yeah, that's our proposed system, and I will explain briefly about the experimental results. So in the experiments, we used the voice conversion challenge dataset, VCC 2020, including several languages and about quite limited data for training and so on for validation and testing. And then for the speech feature, we used 24,000 Hertz sampling rates, and the frame shift was 10 milliseconds, where the processing time per frame is about 8 to 9. And of course, in this case, 9 milliseconds. So we need to get lower processing time per frame compared to 10 milliseconds. But of course, this is quite tight. And in practice, we need to have larger margin. But in this work, the model in this experiment has been able to be used for LLRT. And the total delay was about 33 milliseconds. And to compare the system, we use several models for the sequence modeling and the non-LRT frame-based model, cycle VAE of the VCC 2020. And we compare with the LRT VCC without fine-tuning and with the fine-tuning. I will just briefly show the results for the objective values. There are several measurements, but in the most distinguishable values are, in this case, in the objective measures that the LRT VCCs with fine-tuning, the bottom one for the intralingual and the crosslingual. So the upper table for intra and bottom for crosslingual. And this can improve the oversmoothness, decrease the oversmoothness. So if we optimize the model with the waveform optimization, and then if we look at the accuracy of the speech recognition of the SR, it can be seen that compared to the non-fine-tuned LLRT, it can improve the performance and can be compete with the sequence-based modeling and also the non-LRT modeling. So in our work here, the fine-tuning with the waveform domain improves the LRT VCC performance. And for the subjective evaluation results, what we did is that we measured the naturalness with the 5-scaled opinion score, and then compared to the non-fine-tuned LLRT, it can significantly improve the quality in intra and the cross-lingual. So for the same gender and the cross-gender, and it can also compete with the sequence to sequence, although obviously the sequence to sequence still works better. And for the speaker similarity, it improves, but it's not that significant as the quality, because in practice, the cycle phi can already achieve reasonably good accuracy. What we need is actually more is to improve the quality of the waveform output. So yeah, what we can take from the results is that the proposed LRRT system can compete with and produce reasonably high performance VC. So I will play some samples. Probably there are not so much time. So I will just play the samples for the crosslingual female to female and intralingual female to male. And I will compare the SRTTS, the cycle PAP with WG and with the proposed system. I will play the source female speaker, and then the target, and then the converted samples.
Bismarck serves as a trade and shipping point for an area of large mechanized farms. Wir befinden uns mitten im Verhandlungsprozess. Bismarck serves as a trade and shipping point for an area of large mechanized farms. Bismarck serves as a trade and shipping point for an area of large mechanized farms. Bismarck serves as a trade and shipping point for an area of large mechanized farms. Bismarck serves as a trade and shipping point for an area of large mechanized farms.
This is the target male.
The October crash caused volume to shrink even more. Bismarck serves as a trade and shipping point for an area of large mechanized farms. Bismarck serves as a trade and shipping point for an area of large mechanized farms. Bismarck serves as a trade and shipping point for an area of large mechanized farms. Bismarck serves as a trade and shipping point for an area of large mechanized farms.
So the very bottom is the LRRT with fine tuning, and the target was German female speaker, and then this is the English male speaker. And the speech samples can be heard that the fine tuning can improve compared to the LRRT, and LRRT is degraded compared to the non-LRRT model. And in the case of intralingual, the prosody seems to be better, but the pronunciation somehow it's a bit better in terms of the crosslingual compared to the SRTTS. So finally, I will show several demo for the live demo, and in this demo, the model was built with 62 speakers, more speaker, and I will show several sound samples. And first, I will show a sample from P237 of the VCTK.
This is a very common type of bow, one showing mainly red and yellow with little or no green or blue.
And now,
I'm speaking with the voice of the P237, the converted voice. I will repeat my sentence. A dream, or a dream, that ends in nothing. If the sleeper where they lay down, but very easy to know that you inspired it.
This is a very common type of bow.
So, to my voice.
And then I will show next samples. So this is from the TGF1, the German female speakers.
Ein mürbes Blatt schlürft den Rumpf.
This is the converted voice of my voice. Then I will read the demo sentence. A dream, or a dream that ends in nothing, then leaves the sleeper where I lay down. But I wish you to know that you're inspired.
Ein mürbes Blatt schlürft den Rumpf.
And so, yeah, I will play the final samples from the SLT.
All this day, Gregson remained in the cabin.
And this is a speaker from CMU Arctic.
So, yeah, I speak there, I will read the demo sentence. A dream, or a dream that ends in nothing, then leaves the sleeper where you lay down. But I wish you to know that you're inspired.
All this day, Gregson remained in the cabin.
Yeah, so that's the demonstration of the live demonstration of the VC, and So that's all for the presentation. And for the conclusion of this work, that we have developed the LRRTVC with the cycle-view spectral model and MWP neural vocoder, where we can develop with non-parallel data and obtain a good visual performance. And obviously there are a lot of work to be done, and we want to improve more. We want to improve obviously the quality more and the spectral mapping, and finding several ways more to do that, and several probably out of the box way, not in the usual way. And then we need to also reduce the parameters while still preserving the performance, because we need to consider more lower computational machine, and obviously we want to be able to arbitrarily control the target voice. That's all for presentation. Thank you very much.
Thank you very much for the presentation. We just have a few minutes to squeeze in some questions if people want to use the chat. And as usual in the room, just come up to the front and I'll see you on the video when we switch. I've got a kind of conceptual question about doing this with low latency. Presumably, there's some things you simply can't convert at low latency. So certain prosodic patterns, or I'm thinking of SLT has very particular duration patterns. So it's got slow speaking rate. It's simply not possible to achieve these at low latency.
Right. Yeah, it's obviously depends on the application target. Well, yeah, I actually could not really imagine if you want to really convert the prosody while doing a real-time application, right? But well, that might be like quite. I mean, it's not really convert the prosody in total. Probably, like if you do like conversion like very whole sequence, it might be you might be able to convert the whole patterns, but probably you can extend the the length of the context rather than just one frame, like probably like 70 milliseconds or 60 milliseconds, something like that. And you can somehow convert slightly the prosody, but not that much. So you can still obtain like a longer, prosodic, like prosodical patterns conversion compared to the frame-based. But I think that will be still more tolerable with real-time conversion, I guess. Probably, I'm not quite sure, but yeah.
Sure. Any other questions from the room? So to follow up on the latency, so is there some optimum latency that you're aiming for? Because 0 is unnecessary given sort of limits of human perception. So what is the perfect latency to aim for?
Well, personally, I haven't really tested yet, but in currently about 30 milliseconds seems to be quite okay. But I think it should be like, of course, if we have lower, it's better. But
well, I guess my point is lower is not necessarily better. Below some limit, people won't notice.
Right.
For example, looking at your video frame rate over Zoom now, we're lucky if we're getting 10 frames a second. So your speech and your video only need to be synchronized to within 50, 100 milliseconds. Below that, I can't tell.
Right.
Yeah.
All right. Well, I guess probably I think it should be about 50 milliseconds should be okay. I think it's for real time voice conversion 50 milliseconds. So I guess it's 100. Like probably if you want to do more prosody conversion, 60 to 70, it's a little bit higher, but probably still be okay. But under or about 50 should be fine, I guess. Yeah.
Sure. Okay, last chance for anyone in the chat or in the room. Great. Well, thank you again for a good presentation, and to all the presenters in the session.